Okay, let me repeat the 1D model for multiples. The 1D means we ignore the source receiver distance, so-called offset, okay? We assume source receiver same position, so you only have a vertical variations. So that's called 1D. For the primaries, in the Z transform domain, you know that the Z transform is equivalent to the Fourier transform, okay? So your seismic data after Fourier transform, you can treat it as a Z transform. So when we introduce here the Z transform, basically for the convenience of a discussion. So the primary is the subsurface. It's the water bottom reflection coefficient, R, multiplied by a Z operator. So Z with the power. The power depends on the travel time divided by the delta T, right? So it's the index, if you recall that. And the multiples, the first order multiple, basically this same travel feature, travel behavior, doubled, right? That's the first order multiple. One RZ prime, another RZ prime, and on the surface here, the reflectivity is -1. So you end up minus RZ prime squared. That's first order. The second order, in the front of the first order, pre-multiply another one. It's a -1 here and the RZ prime. So you have a RZ prime cubic, right? So for the high orders, simply you just RZ prime with a power here. It is interesting to see this seismic data, seismic trace is a convolution of the primary with a multiple filter, a filter of multiples, right? The filter of multiples is a polynomial. This polynomial is Z transform, right? And this is Taylor expansion of 1 over 1 plus RZ prime. So the filter of multiple is 1 over 1 plus RZ prime. The inverse filter of multiple is basically the denominator, 1 plus R prime, right? So now if we apply this to your data, that means this part multiplied by this will be cancel each other, right? Those two will be canceled. And they end up the primary. So you can see multiple removal by inverse filtering. Your inverse filtering, use this inverse filter to your data. You cancel this multiple filter. You end up primary. You can see that's the mechanism here. Right. That was talking about the water bottom multiple, water layer, and the water bottom, right? For the subsurface structure, you can have also have a similar multiples. Let's see one example here. If I have a reflector here, as I said, reflector different from refraction, right? Refraction is in the data domain. It's in your seismic data. Reflector is in the model space. It's basically the physics model, right? So you have source here, travels through the water bottom and reach to this reflector and then come back upwards to the surface. That's the primary. That's the primary reflection from this reflector. You can represent it as a reflection coefficient R double prime, which means the reflection coefficient of this layer. And the Z double prime, which means the Z with the power of, depends on this travel distance. This power is the travel distance divided by delta Z, because the index of time samples, right? So this is a primary. Talking about the multiples. If a water layer multiple in the front, we call the Pegleg multiple. But basically, what's Pegleg means one shorter, one longer. Right? It's called Pegleg. Right? So that means when we have a primary from this reflector, but also multiples from water layer, so your wave actually from source to the water bottom, reflect to the surface, come back down, going to the reflector, going back to surface. Okay? So you pre-multiply by minus r z prime. Minus r, minus means here. And the r is here, right? Okay. Second order Pegleg, basically the wave bouncing in the water layer twice. That's the source side. In the source side. So this is the reflection of this layer, and those are the multiples. Okay. So Pegleg multiple in the source side can be presented as a PZ, which is primary, convolved with a field of multiples. First order, second order. Right? Again, this time series, this polynomial can be treated as a Taylor expansion of 1 over 1 plus r z prime. Okay. Inverse field is simply the denominator of this, will be 1 plus r z prime. If you apply this inverse filter to your Seismology data, you will remove the effective multiples. You end up the primary only, right? Make sense? Okay. Again, because R is a reflection coefficient of a water bottom, R is less than 1. So this filter is a minimum phase filter. So you can, of course, you can do the inverse filtering, right? So filter for multiple under the inverse filter, both are minimum phase. For the receiver side, almost identical. There's a Peglegs in the receiver side. That's the first order water bottom multiple, water layer multiple. So the primary of this reflection and post multiply by first order multiple, which is water layer. Minus means the reflectivity on the surface, water surface, and the R is the reflectivity of water bottom, right? And the second order receiver side of Peglegs. Peglegs really means this part, the length is different from this, right? So that's the second order Pegleg multiples. Same as the source side, identical. You have a receiver, I have a primary here, convolved with a multiple filter. The multiple filter in the receiver side is 1 over 1 plus RZ prime. The inverse filter is 1 plus RZ prime, basically the denominator of here, right? So if we apply this filter, apply the inverse filter to your data, you will cancel the multiples and end up primary. Again, both the filter for multiple and the inverse filter are minimum phase, right? Identical. Okay, but why I describe these two cases separately? Because this involves assumption. The assumption is the water bottom here. We said it's a source receiver, a same position is 1D, right? 1D means this point actually the same point. Otherwise, if we consider the offset, water bottle may be not flat. If we have a dipping angle, so source side and the receive side multiples will not be identical. You see that? Okay. So that's actually limitation of a particular decon. Right. That was source side Peglegs, receive side Peglegs. Maybe you have mixtured. You have a source side, receive side. Right? Because it's a one, I emphasize, it's a 1D model. Either source side or receive side, they have the same effects, right? So that's the source side multiple, receive side multiple. The same thing, the data, the seismic trace is composed of multiple in the source side, primary, and the multiple in the receiver side. Okay. Right. For the source side, you have a 1 over r, 1 over 1 plus r z prime. For the receiver side, you also have a 1 over 1 plus rz prime, because you now have both source side and the receiver side. So here it's squared, right? So 1 over 1 plus rz prime squared, right? For source side, if we go back to see the previous slides, for source side, 1 over 1 plus rz prime, right? Receive side, now we have both source side and receive side, so effect will double. It means you have squared here, right? So for both source side and receive side, the Pegleg multiples is 1 over 1 plus rz prime squared. The inverse of that, the inverse filter is the denominator. Simply is 1 plus rz prime squared. Apply this to your data, you end up, you cancel the filter multiple filter from in the source side, you cancel the filter multiple in the receiver side, right? So you end up only the primary. Can see that? Now, again, the inverse filter is a minimum phase, of course, because the multiple filter is a minimum phase, basically because R here is smaller than 1. Quite often much smaller than 1, right? So that's guaranteed a minimum phase. Okay. Now, let's go, after review the multiples, we said one of the objective for the predictive decon is to remove multiple, right? One of the applications, okay? Now, what is predictive deconvolution? So the key word is predictive. That means the signal or multiples is predictable. That means in your data, in the seismic trace, you have something really periodic predictable, okay? The purpose is try to remove those events which are predictable in the time. We saw that for multiples, because they have fixed travel time and almost fixed wavelet, so they can predict it from seismic data. There are two options. One, the subsurface reflectivity series is in white, so randomly distributed. That's important. If we talk about single layer, maybe it doesn't work, right? But if you have a multiple layers, many layers, subsurface, that will work. So that means your seismic trace must have a certain duration, must have a certain length. Otherwise, this method doesn't work. Okay. Assume a minimum phase, that's no problem. In the marine environment, subsurface reflectivity is less than 1, so that's minimum phase. Okay. Now, for multiple prediction, because we know the multiple is in a certain time, so there's a gap in the prediction. That means we keep the first part untouched, and then only remove something periodically in the long period, right? So that means this method also called a gap deconvolution. That means in the predictive decon, there are two parameters. One is the gap, which means this part next to zero leg were untouched, you keep that. Another one is filter length as a spark decon, right? Let's see how the autocorrelation works for the predictive decon. Autocorrelation, we said, for the general seismic trace, autocorrelation contains information on source signature, autocorrelation, and the subsurface reflectivities, and also the multiples now, right? In the previous slides, we didn't talk about, but now we're talking about also multiples. Okay, now let's see how it works. Autocorrelation over a seismic trace in the Z transform domain or in the Fourier transform domain, it is a multiplication of a spectrum with its complex conjugate. That's autocorrelation. That's the data, seismic trace. After the autocorrelation on the right-hand side, there was elements called E converted by E complex conjugate, right? Sorry, E multiplied by E complex conjugate, which is the reflectivities, because we assume the reflectivities is in wide, so that means E multiplied by E complex conjugate becomes 1 here, so you just remove that. But now you have multiples, not only the wavelet, so the autocorrelation here, not only the autocorrelation of wavelet, which is W multiplied by complex conjugate of W, but also the autocorrelation for multiples, which is M and the M complex conjugate, right? That's different from the previous slides. Previously, we said after autocorrelation, we only have a wavelet. We assume your seismic data autocorrelation to be equivalent to the autocorrelation of wavelet, right? But now, in fact, your autocorrelation here, when you have multiples, your autocorrelation becomes autocorrelation of wavelet and autocorrelation of multiples. They're multiplied together. The modification in the Z transform domain or in the frequency domain really means really equivalent to the time domain as a convolution, okay? So the autocorrelation here really means in the time domain, it's a wavelet autocorrelation convolved with the multiples, with the autocorrelation of multiples. Okay, modification is convolution. Now, how we do the deconvolution? Before that, we need to understand the parameters. After the autocorrelation, your autocorrelation coefficient looks like this, variables t. So the zero leg, you have a peak here, and you have a multiple here, because the first order multiple, if we correlate to the primary, they're almost identical, slightly smaller. But remember, you have a minus R because you have -1 on the surface. So that means the priority here is opposite, right? And the second order multiple primary, the priority also opposite. So you have a first leg, which is a primary, first order multiple, second order multiple. Can you see that? So this basically periodical. You know the period here. That's different multiples, okay? Right. So the first part of this one we should keep because there's nothing to do with the multiples. We try to get rid of the multiple really means we try to get rid of the first leg, second leg. If after autocorrelation, you will see these two trough or peak disappear. That's what we want to do. So this gives us the indication, the guidance how to set up the parameters for the autocorrelation, for the gap decount. So the autocorrelation of our original seismic trace was the peak here at 0 leg and the multiples, and then second order multiples, maybe high order multiples, but gradually disappear, right? No. After your desirable output will be look like this. After the deconvolution, if we do autocorrelation, you will see the first part, which is a source signature, the WZ, were untouched. So we keep this untouched, right? So this is called gap. Gap means you from time 0 to here, you will not do anything. You have a gap here. And then you have another parameter called filter length or operator length, right? So for predictive decount or gap decount, they have two parameters. One's gap, one's operation length, okay? So after that, this multiples, this first order, second, they will disappear. That's in the autocorrelation display. The gap here must be wide enough to try to keep the source signature untouched. If too small, will damage the signature. You try to keep it because your hopes here is to get rid of multiple. So now let's compare the two deconvolutions. One's spark decount, one's predictive decount, right? The purpose of predictive decount is targeted at the multiples, right? Try to avoid the damage to the signature, okay? But for spark decount, it's targeted at the wavelet, target at the signature, right? Of course, the wavelet can include some very short period of multiple, which like bubbles, right next to the airgun. We can unify these two deconvolution by, we assume they're both controlled by a gap. So spark decount is also can be treated as a predictive decount, but in this case, the gap is only one unit, one sample, the first one, spark, right? So now we can unify these two deconvolution. In fact, in this commercial software, spark decount and the predictive decount, there's single software. It just depends on the setup of a gap. If gap is single sample, that's the functionality is spark decount. If gap is not single, it's not a single sample, it's a certain number of samples, that's called a gap decount or predictive decount, right? So gap decount is a uniform terminology for two deconvolutions. Okay. Let's show you some examples. Remember, there's one assumption here. We assume the acquisition geometry is 1D, which means we ignore source receiver distance, right? So this method may be failed because if source receiver distance cannot be ignored, right? Let's see. Nevertheless, let's see how it works. There are four shortgetters, so-called shortgetters. Basically, they are series receivers recorded the signal from the same shot, right? And the first arrivals have a different time, which means the source receiver offset is different, right? The later arrival means the source receiver distance is larger, okay? So you have four shots here. As we said in the deconvolution, either spark decon or predictive decon, one of the purposes is we try to see some effects in the autocorrelation. Okay, so here, the bottom here is the image of autocorrelation. You can see here you have the zero leg is not plotted at zero. They have a delivery time delayed a little bit, right? You can see. So that means you can see the full form of zero leg. Okay, so it's slight shift. We know exactly how much shift. So we have a zero leg, but also have multiples behind it. So between the first zero leg and the first arrival here, that's actually is the time period of a multiple, right? Okay. So spark decon applied to seismic data trace by trace. One trace. How do we apply that? We have 3 steps. First step, we transfer seismic trace to the frequency domain by FFT, fast Fourier transform. And then we multiply the Fourier transform by a filter, which is the one called spark decon filter, right? And then we do the inverse Fourier transform. So all the 3 steps. So you do the process trace by trace. That's not the multi-channel production. That's a single trace production, okay? Right. On the right-hand side here, this example with 250 millisecond filter length. The gap is a spark, right? So the so-called spark decon. So gap is 1 sample, and the filter length 250. Okay, let's see the result from autocorrelation. You can see, compare these 2 autocorrelations. For after spark decon, you keep the first zero leg almost untouched, but the multiples here disappear, right? See it? This is not necessarily the subsurface multiple, but maybe the bubbles or ghost in the near surface, in the next to the air gun, right, or next receiver. So this could be remove the ghost. Could be, right? Okay. So this is the straightforward display visualization of spark decon. If we go back, if we see the short gathers, you can see here we have multiples here, but after the deconvolution, you can see much cleaner here, right? Okay. So, for example, you have a strong reflection here that could be the multiples of layer with a weak subsurface reflection, but after removing multiples, you can see the weak reflection come up. So that's very good result of spark decon. If we see the same process but with different parameters, you can see what happens. For spark decon, if we set up the filter length 60 milliseconds rather than 250 milliseconds, so it's a short wavelet, it's shorter filter length. You can see here, this autocorrelation, zero leg untouched, and between the zero leg and here the multiples inside much clearer. However, this multiple here actually still here, right? So that means this 60 milliseconds filter length is too short. Let's go back to the previous one. You can see here, that one. Removed this leg autocorrelation, right? But now, this one's still here. In your seismic gather, You can see that's the multiple here, but still here, right? You can slightly reshape the signature, but seems the multiple still here, right? Or the short period multiple still here. All right, that's too short. Seems that's not effective. Operator too short, right? If the operator too long, the operator is too long, okay, you have the zero leg perfect here, but also remove everything underneath. That's the autocorrelation. And from your seismic profile, for example, here, you not only remove multiple, and also this weak reflections becomes even weak. Well, it's relative because your first arrivals untouched, right? And then this part of energy become relatively weak, okay? So you need to test the filter length by comparison and set up the optimal one. There's no quantitative way to do that. You best just run the visualization of autocorrelation. Right. It was on the pre-stack gathers. If we will apply this to a stack section, what stack means, at the moment we haven't introduced how to do stack, but now we just simply assume all these traces can be somehow summed together. The assumption here, the Pop's assumption here is try to enhance the coherent events. Coherent events means signal. But by assumption, if something is incoherent, if some of them will, the assumption will reduce that incoherent events, right? So you can think about the stack here as an enhancement to the signal, and for the attenuation of incoherent event. So the stack section looks like this. You have a water bottom. It's not flat, right? As we said, maybe the 1D assumption not good, but if source receiver assume the same point, and the reflector point maybe it's not vertically exactly below the source receiver position, but maybe have a slight angle, but still 1D. After the spark decon with a 250 millisecond filter length, the result look like this. So let's start with the visualization of autocorrelation. Before deconvolution, you have a zero leg and the dominant period here. After deconvolution, you keep the zero leg much narrowed, right? In terms of autocorrelation, much narrowed. If you see the detail here, much narrowed. And also, you get rid of dominant period signal here, which could be the multiple, right? That's and in your stack section here, you have a strong multiples, but after that you can see the weak refractions and also a fault here come out. Okay. Of course, this is not the best result because we have a 1D assumption here. However, the subsurface structure is not a 1D. You can see it is not flat. And the subsurface, the water bottom is not flat, the subsurface structure is not flat, so it's 1D, won't work. And the source receiver also not zero. Source and receiver offset is not zero, right? So 1D has some effect, but not perfect. That's the case. Nevertheless, if we compare this result with the wavelet with the filter too short or too long, that's too short. If it's too short, you can see we of course we narrowed the zero lag autocorrelation. It's much narrower. This one's wide vertically, but it's narrower. And you have effects between the zero lag and the first dominant period. In between, you can wide up, but here you have something inside. You can see that, but no, so actually you have effect to remove, to wipe out, to zero out the inside. Right? That's perfect. But this period is still here. So that means this sequence is saying if you see the dominant energy, like this, the multiples is still here. If it's too long, you have the zero lag autocorrelation narrower compared to this one. Also, the first dominant period also attenuated, and more importantly, this part also attenuated. Right? You can see here, this one, this dipping event here almost gone. Right? We wipe out. This dipping event is not a multiples. You should keep it because this is actually strictly related. So that's too long. Okay, if we go back, actually the ideal one in this case is this parameter. Spark decon, the gap is 1, and the filter length is 250 milliseconds. Compared to the gap decon, compared to the predictive decon, same for short gathers. If we use gap decon, okay, this is the autocorrelation of original short gather. Now with a gap decon, predictive decon. Right, predictive decon means because we use a gap, the gap means we keep this part of a signature untouched. So the first leg, the zero leg autocorrelation would be identical to the original one because inside it's keep untouched, right? However, the multiples like here will be completely zero out. So predictive decon removes the multiples. In this example here, the gap is 32 milliseconds, and the field length same as spark decon 250 milliseconds. So the spark decon gives us the suggestion for the field length, but the gap decon here we have a gap 32, which is at the period untouched. We also show different results with a different, well, of course, 60 milliseconds is too short, right? But now if for 600 milliseconds is too long, you can see here, that was somehow after the multiple, this parameter becomes much weaker because, first arrivals relative becomes stronger, right? So that's the field length is too long. That's the problem, okay? That was application in the pre-stack short gathers. So we can compare this result after stacking, right? But even this stack section here, but the application is before stack. DBS means deconvolution applied before stack. So basically we apply to the short gather. So really means this stack section is not a result of straightforward from here by deconvolution. No, it's from here. So you have original data and then you do a predictive decon, and then you based on this predictive decon result, you generate stack section, okay? So this is the deconvolution before stack, okay, DBS. Parameters are 250 milliseconds and 32 milliseconds, right? We already showed that before. And on the stack section, you can see very clearly the zero lag autocorrelation identical to the zero lag autocorrelation of our original stack. the multiples completely removed, right? And after removal, the multiples, you can see this dipping structure here. You know, waterfall means this dipping angle, but that's opposite to that. There's definitely the subsurface structure, right? Maybe there's a small multiples. I mean the short period multiples within this layer, right? Okay. You will ask me, what's this here? What's this here? Anybody know what's this here? Because I said structure look like that, but what is this here? Anybody know that? That is the residual for multiples. Okay, how to recognize that? Because this is the water bottom. We said the multiple have a constant periodical time, right? So here, if we doubled, that's 800 milliseconds, doubled 1.7, so will be something here, and tripled will be here. Okay, because but this is not exactly the flat one. You have a dipping angle, so this one here. Okay, so that means this result tells us two things. One, predictive decon works, but it's not always works. It's not always working, right? Depends whether the condition, whether the situation satisfied one-dimensional assumption. That's the important thing, right? Compared to 600 milliseconds, we read some details here. Because here you can see much less details, right? Because you remove something down underneath here. Okay, it's subtle here. And if you have a different display, you can zoom in to see the details. We are talking about this deconvolution, talking about multiple removal in the latest sessions, right? In more detail, typically for non-zero offset, for the not 1D case. Right. Issues with the predictive decon. We already said that actually. Let me summarize that. First of all, the multiples may not periodic for non-zero offset. Right? If even for the water layer multiple, if water bottom is not flat, water bottom is not flat, so the multiples may not be periodic, right? In deeper water layer, you have a longer travel distance, longer travel distance, and longer travel time. In the shallow water layer, you have a short travel time, right? So it's not periodical. And deconvolution here assume amplitude is plane wave, which means only we're talking about frequency by frequency, right? So in the same frequency, they have a periodic. That's called a plane wave, right? So there's no interaction between different frequencies. The third issue is the subsurface refractive is not always wide. Basically depends on how many layers, how deep your structure you consider, how deep the structure you consider, okay? Earth is not 1D, so conclusion is it's not always successful. That's the issues. All these issues we'll deal with in the later sessions in this course, right? So let's summarize what we learned today for the last 3 hours. Okay, let me repeat. First of all, we review the Z transform domain typically in the context of convolution and the correlation, right? Okay, and then we introduce the concepts of filters, including filter itself and the inverse filter. Okay, they're actually both are the filters, but just talking about the one is the inverse of another one, right? That's the thing. And for the success of an inverse filter, we do need the filter itself be minimized, be minimal phased, right? So we introduce difference between the filters by minimum phase, maximum phase, or mixed phase, right? So we need use the equivalent field concept to transfer each of this maximum phase, minimum phase, each dipoles into minimum phase dipoles, and then you can do the inverse, right? The pop scale try to do the inverse. And the issues, because application of a filter most likely for seismic deposit in the frequency domain, in the Z transform domain, so that means involves fast Fourier transform. The fast Fourier transform, you need zero padding to make it, the length, total length becomes a half of 2. Zero padding also try to avoid the wraparound, because in the Fourier transform, there's an assumption implicitly. You assume that your seismic sequence is periodic, right? If we have enough zero padding, so that means you can separate different period. But if not, if zero padding is not sufficient, that means the periodic series will be overlapped partially. That's the wraparound. For the filter, there's a Gibbs phenomenon. Generally, Gibbs phenomenon have a leakage in the suppression band, but also the top of amplitude spectrum is not flat. It's not always one, right? You can enhance part of a frequency, suppress part of frequency, right? Okay. Another thing, when we're talking about inverse filter, if the frequency component is 0, you cannot do inverse. While 1/0 is not exist or not stable. So you do need a so-called pre-whitening. Pre-whitening means you assume there are some noise, and the noise is white noise, which means zero lag of noise is a constant. So you can add in a constant to the zero lag of autocorrelation of seismic data. That's called pre-whitening. In terms of this square, this pre-whitening means a stabilization factor, or means the model constraint, okay? And these squares really means we try to generate filter and apply filter to the data. The result will be approximation, not exactly the desired output, okay? So this square means you try to have a minimal error energy. The error means the difference between your approximation and the true ideal output. Okay, so that's these squares. And there are two applications, these squares. One is called spark deconvolution. The purpose of that is to shaping the wavelet, make it a more narrow, more spark. And the predictive decon in here, we just introduce here, mainly for remove periodical signals, which is multiples, right? Both deconvolution can be treated as a gap decon. The difference between the two is, first one, the gap is one sample. The second one, the gap definitely is the gap you want to keep all the signals untouched, right? So that's the difference. Right, I think we finish today's session.